The General Principle of Relativity in its Philosophical and Historical Aspect by Herbert, Wildon, Carr. Chapter 2. Einstein's Theory. It is not only in its importance and in the extent of the revolution it affects in our worldview that Einstein's theory is comparable with the Copernican discovery. There is a striking similarity in the nature of the two. It is difficult for us today to realize that to the pre-Copernican world, even to its most reflective minds, the celestial movements presented no problem, certainly nothing in the nature of a dilemma. No one had doubted, why should anyone have doubted, that the movements observed in the firmament were real movements, whatever complications might be due to perspective. Suppose one had doubted it. To what possible criterion could he have appealed to resolve his doubt? No court of appeal is superior to direct and immediate sense intuition and able, therefore, to overthrow actual perceptions by judgments. If, then, the alternative interpretation had occurred to anyone, as it did in fact occur to Copernicus, that the movements we perceive are not real movements at all, but only appearances of movements, illusions produced by a real movement which we do not and cannot perceive, it must have appeared in the highest degree fantastic, extravagant, and absurd. Not on account of childish puzzles, such as the reversal of position at the antipodes, but on account of the purely philosophical difficulty that we can only overthrow an accepted criterion by replacing it with a more authoritative one. To the pre-Copernican world it seemed, and must have seemed, that there can be no more authoritative criterion. Demonstration to sense was the highest certainty, and indeed the ground of all certainty, even in matters of religion. Was not Christianity established and confirmed by it, and does it not depend on it? Was it not by the signs and wonders which he did that Jesus gave evidence of his divine mission? Every consideration, in fact, which a cultured mind in the time of Copernicus could have brought to the Copernican theory must have tended to strengthen the universal opinion that it was extravagantly improbable. And extravagantly improbable it would have remained had the telescope not been invented, which, some half-century later, enabled Galileo to make the observations and experiments founded upon observations which could only be consistently interpreted by adopting the speculative monk's hypothesis. There are many facts of ordinary everyday experience, the interpretation of which is so direct and self-evident and seemingly rooted in the nature of the fact that the possibility of an alternative interpretation rarely suggests itself even to the speculative mind of a philosopher. Yet there may be an alternative, and should it occur to a man of genius, it may throw a flood of light on the mystery of the cosmos. Let me illustrate what I mean by some commonplace examples. When iron filings are scattered on a plate and a magnet is brought near enough, the filings at once assume a definite and orderly arrangement. No one hesitates for a moment as to what is the natural interpretation. We say at once that the filings are magnetized, and by this we mean that the magnet has so changed the nature of the filings that they now behave differently and in a specific manner. Yet there is an alternative interpretation. It is possible that the nature of the filings and anything we can describe as their quality or as a property of them may not have been changed or modified in any way whatever, but that what is changed or modified is the space which they occupy. This space may be curved or strained in the neighborhood of the magnet, or as we say, in the magnetic field, so that the arrangement of the filings is automatically altered with no more interference with their nature than there is a change in our face when its reflection is distorted in a curved mirror. Why does the one interpretation appear natural and rational and suggest itself instinctively, while the other appears strange, if not actually inconceivable? The answer is obvious. We conceive space as an extension or void which has no structure. We find it easy, therefore, to imagine iron changing its properties, but impossible to imagine space changing its nature. So too, in like manner, to take an example from everyday experience, we all know that it is dangerous to alight from a train while it is in motion, and that the danger is proportionate to the velocity of the train. We find no difficulty in interpreting this. It seems obvious and self-evident that the movement of the train must engender a habit in us which renders us incapable of suddenly adapting ourselves and assuming the upright position on the non-moving platform. On reflection, it may not appear a very rational interpretation, and it is certainly not what anyone without the experience would predict. But there is the fact, and we do not hesitate for a moment as to what is the interpretation. Yet there is an alternative. It may be that the space of the non-moving system is deformed, and that when we enter it from the moving system, the direction of our movement is changed automatically. The unpleasant result would then not be due to any change induced in us by the movement, but to the structure of the space system. Now suppose that such an alternative interpretation, notwithstanding its extravagance, should do no more than throw doubt on our concept of space, and suppose further that a new concept of space should be found to harmonize interpretations formerly irrational. We should very soon come to adopt the new concept and apply the new interpretation. We may see, then, that however self-evident to common sense and apparently based on intuition, the interpretation of common facts of experience, such as those instanced, may be, and however extravagant and purely speculative any possible alternative interpretation may appear, should it be possible to show that the alternative interpretation accords with observational and experimental fact, it may become as natural to common sense as it was formerly irrational. This is what actually happened in the case of the Copernican discovery, and it is what is happening in the case of the Einstein theory. The illustrations, which are only illustrations and not particular instances, have been chosen in order to indicate not only the principle but the general nature of the theory. Our common mode of interpreting the curved paths of masses moving relatively to one another as the result of the action and interaction of forces of attraction and repulsion exercised by the masses across the distance separating them is irrational in theory and false in fact. The true interpretation is that the track of every moving body is primarily determined by the geometry of the system. Thus, if a horse is being exercised in a field by a man in the center who holds it with a long tether, its circular movement is not determined by an influence or attraction exercised by the man, nor is it due to the horse's choice of direction. It is the simple consequence of the necessity imposed on the horse and the degree of freedom allowed to it by the whole system. Suppose the horse to be unaware of the cord by which it is tethered, and unobservant of the outside world, and exercising its freedom of movement, it will be, from its own standpoint, going on in a straight line, and only an independent observer will know that the line is a circle. This may illustrate also the other and complementary part of the theory. If it is the structure of a system which determines the direction of the movements in it, there must be some subjective principle by which we possess ourselves of a standard or criterion. There is such a principle, and it is of fundamental importance in Einstein's theory. Every observer of nature coordinates the universe from the standpoint of his own system of reference, that to which he is himself attached. For him, it is a system at rest. This does not mean that he chooses arbitrarily that it shall be so, or that he finds it convenient to think it so, or even that he finds it necessary to think it so. The importance of the principle lies in the fact that there is no choice in the matter. It is the fundamental condition of science. It shows us why, while we can calculate the movement of our system, the Earth, we cannot by any means experience it. Thus, while by observing the celestial movements and transforming them into corresponding movements of the Earth relatively to the observed celestial movements, which we then consider to be systems at rest, we may know with scientific accuracy and practical certainty that we are being translated through space at the velocity of some 5,000 miles a minute. We have no means by which, closing our eyes on the heavens, we can be aware of our translation. To revert to the previous illustration, if we suppose the horse to be unaware of the tether and unobservant of the environment, nothing in its own actual experience could reveal to it that it was not moving freely in a straight line, but traveling round and round in a circle. The new theory, then, is twofold, or perhaps it would be better to say has two aspects, one objective, one subjective. The one concerns especially the concept of scientific reality, the other the method of scientific research. In the first place, the theory affirms that all the events which we observe are only to be interpreted by the geometry of the system to which we refer them. In the second place, it affirms that for every observer the system to which he himself belongs is absolute, in the sense that the coordinates he uses refer to that system. We can only measure the movement of any system by taking our own system to be at rest. The significance of the theory is therefore seen to be centered on the concept of the system of reference. A system of reference is any space-time continuum which can be regarded as at rest in relation to systems which are moving. There are two characteristics of a system of reference. The first is that the time dimension is not independent of the space dimensions. That is, the order of succession of its instants is not independent of the order of juxtaposition of its points. Not only is there no space without time and no time without space, but every event is coordinated by four axes of coordination, 3 spatial and 1 temporal, and they are equally covariant. In the older theory, that of the classical mechanics, every point of space was fixed absolutely with regard to every other point by 3 coordinates, known as the Cartesian coordinates. To measure movement, it was necessary to introduce time, but time was treated as an independent variable. The second characteristic is that every space-time system has its own geometry, and there is no universal geometry of an absolute system. The first of these characteristics is perhaps most strikingly shown in the different signs used. In the older theory, mathematicians wrote the signs for the 4 axes of coordination as x, y, z for the space, and t for the time. In the new theory, the signs are x1, x2, x3, x4, thus indicating that each axis is covariant with the others. The second characteristic is most marked in the dethronement of the space of Euclid's elements. Instead of having to postulate it as a substratum underlying material systems, Euclid's geometry is now said to apply only to a system imagined infinitely remote from all material systems. Euclid's propositions are true of a space system in which curvature is zero. In the new theory, wherever there is matter, there is curvature. To understand Einstein's theory, we must see how it was arrived at. I have emphasized its twofold character, and we find that there are two lines of speculation which converge in the theory. One is distinctly philosophical, though not the work of philosophers. It is the recognition by physicists of the importance in physical science of having regard to the psychological origin of the data of physics. The other is distinctly mathematical and is represented by the work of the mathematicians of the 19th century in evolving and formulating the non-Euclidean geometries. But before we can appreciate the significance of these movements, we must understand the device by which the old theory harmonized the complexities and discrepancies of sense experience. Suppose, then, that a traveler on a railway journey, comfortably settled in his carriage, strikes first one match, then another, to light his cigar, and that the successive flashes are observable events from any position in the universe. To the traveler himself, the two flashes occur in the same place and are only separated by a time interval. To an observer not in the train, they are separated in space by the distance the train has traveled in the time interval. To an observer on the sun, they are separated further by the distance the Earth has traveled on its orbit. To an observer on Sirius, by the distance the solar system has moved, and so on. Again, for the observer on the sun, the flashes will occur some 8 minutes later than for the observer on the Earth, and some 8 years later for the observer on Sirius. And also the interval between the flashes will depend on the distance separating them in space. How are these complexities and discrepancies harmonized? By the device of assuming an immobile system in which all the movements, including that of the propagation of the flashes of light, are contained, and in relation to which the velocities of these movements are absolute. This becomes the concept of a homogeneous space, which can never be an object of sense perception, but which can be and is an intelligible object, and whose intelligible qualities are the subject matter of geometry. Euclid's definitions and axioms and postulates and the propositions based on them apply exclusively to these intelligible qualities of a conceptual space. But to see how arbitrary the procedure is, we must criticize the way in which, by what seems to us a natural reasoning, we first form the concept of absolute space and then affirm its objective reality. We are unable to believe that the space which we know by sight and touch is real space, or that the propositions of geometry apply to it, because our immediate experience is of changing perspectives. Yet, while things alter in appearance as we change our position, we are able imaginatively to transform the perspective in which things appear from one position into that in which they would appear from any other. Hence arises the notion of a pure space devoid of any perspective, unperceived and imperceptible, underlying and supporting the infinite perspectives. In exactly the same way, the sensible qualities of the objects which alone we experience gave rise in philosophy to the notion of a substance which we do not experience, but in which the qualities inhere. In the one case, as in the other, no sooner is the skeptical inquiry of the philosopher directed on the notion than its baselessness is evident. But there is a necessity of practical life more important to us and more compelling than the theoretical argument of the philosopher. We find, in fact, that we very soon reach the limit of sensible discrimination. No one trusts the senses, or depends upon them for accurate measurement. Would anyone, for example, be satisfied that 2 packets of tea weigh the same because it is impossible when they are balanced in the hands to detect a difference? We are continually inventing and improving the inventions of instruments which extend the range of sense discrimination far beyond the natural range. How can we rationalize the apparently indefinite limit of this extension otherwise than by assuming an absolute mathematical continuum in which the point without magnitude is 0? Hence it comes that the coordination of the universe on an objective and absolute basis, independent of changing experience and varying perspective, appears as the rationalization of experience itself, as the only basis of scientific reality, and as a necessity of the practical life. Were doubt in regard to the existence of an absolute mathematical continuum purely speculative, it would exercise little influence on the reform of scientific method. Doubt has come, however, not only from philosophy, but from science. It has 2 sources. It comes first from the physicists who have investigated the problem of the psychological origin of the data of physics, and second, from the mathematicians who have investigated the logical dependence of geometry on its postulates. The most representative name among the physicists who have concentrated attention upon the epistemological problem insofar as it affects scientific method is Ernst Mach, 1838 to 1960. He does not stand alone. Many others deserve mention, and particularly W. K. Clifford, and later Karl Pearson in England. But Mach appears to have had a direct influence upon Einstein. The problem which engaged him may be described as the application of the principles of Berkeley and Hume to the actual work which the physicist does in his scientific research. The keynote of his theory concerning the nature of scientific truth and the method of scientific inquiry is to be found in the term anti-metaphysical, which he inscribed at the beginning of his chief work, The Analysis of Sensations. I will illustrate his idea in my own way. Our knowledge of nature is primarily our sensations. These give us perceptions. Our perceptions are of blue skies, crimson sunsets, green fields, singing birds and buzzing insects, and such like, but they all consist of various combinations of tastes, smells, sights, sounds, touches, and can be analyzed into them. Our scientific inquiry leads us to form concepts of physical realities. What we perceive as color, we conceive as a frequency and amplitude of ether vibrations. What we perceive as warmth or heat or cold, we conceive as varying velocities of the movements of molecules. The reality we conceive is therefore fundamentally different in its nature from its quality in sense experience. In what way, then, are the concepts of physics interpretive of the experience? The ordinary notion is that the sensations are simply the subjective appearances of the physical realities we conceive, and that we interpret our experience with all its aesthetic quality of color, sound, taste, smell, touch, by the notions of substance and cause. That is to say, we suppose the physical realities to be substances possessing sensible qualities and causing sensations. This is the scientific theory which Mach denounced as metaphysics. He criticized it as a method and declared it to be wholly unscientific. Physics has no need of the concepts of substance and cause, and to the extent to which we employ them, we darken instead of illuminating research. The data and whole subject matter of science are sensations, and the true method of science is analysis. It is from analysis of sensations that we obtain our concepts of the realities of physics, and when by abstraction we infer in them an order independent of the order of sense experience whence we derive them, it is illegitimate to set up the physical order as standing in a causal relation of interaction with the psychical order. The most that we are entitled to affirm is that the two orders are parallel. The importance of this doctrine in relation to Einstein's theory is evident. Physics can point out no royal road by which we can get past the immediate data of sense and find ourselves transported straightway into a world of absolute existences, a world of realities independent of their appearances to finite subjects of experience. It elucidates, therefore, the side of Einstein's theory which affirms the absoluteness of the frame of reference to which the observer is attached, that is, the necessity which makes the observer's system a system at rest. Even more important and more direct in its influence is the criticism of the postulates of geometry. This is a long chapter in the history of mathematics, and I can only indicate its general nature. 3 names may be taken as representative of 3 distinct stages in the evolution of the new concept of the science of geometry. Gauss, 1777 to 1855, Lobachevsky, 1793 to 1856, and Riemann, 1826 to 1866. Everyone is familiar with the difficulty of mapping a spherical surface on a flat sheet of paper. The schoolboy's atlas of geography illustrates its nature. Whether the maps are drawn on the principle of Mercator's projection or by the more ordinary method of curved parallels for the lines of longitude and latitude, in either case they involve distortion, because a spherical surface, however slight be the curvature, cannot be flattened out or made to fit point to point on a rectangular plane. Gauss's problem was to find a mathematical formula which would determine the position of any point on a spherical surface. The Cartesian coordinates had accomplished this for rectangular space in 3 dimensions. Curvature, however, introduced what is practically a new dimension, and Gauss set himself to discover the means of dealing with curvature. As curvature admits of degree, his formula had to be adaptable. The coordinates he invented are known by his name. What is more remarkable, however, than his success, and even more significant, is the kind of doubt with which he started and the means he devised of bringing it to a test. It indicates the beginning of doubt as to the physical reality of the absolute mathematical continuum of Euclid's geometry. Gauss began by devising means of measuring very large geometrical figures, triangles, whose sides were miles in length, in order to see whether they conformed to the properties they ought to have according to Euclid's demonstrations. Whether, for example, their 3 angles would prove to be equal to 2 right angles. He obtained no results of any value. The means at his disposal, light signals from mountaintops and reflecting mirrors could not be adequate for the detection of a difference we now know to be infinitesimal. Yet we see in those experiments the first beginnings of a doubt whether light rays may not be deflected from the Euclidean straight line by reason of the curvature of space. Lobachevsky dealt with a different and much older problem, Euclid's postulate of parallelism. The postulate requires us to grant that through any point outside a given straight line, one and only one parallel straight line can be drawn. From classical times, it has seemed to mathematicians unsatisfactory that this should be a postulate. It purports to be a truth which follows from the nature of the straight line, and ought therefore to be capable of demonstration, to be in fact a proposition like any other, and deducible from the postulate of the straight line alone. Many attempts to give such a demonstration have been made, but none successfully. The whole problem entered on a new phase when Lobachevsky, a Russian mathematician, and by a coincidence a Hungarian mathematician, Bolyai, working independently on similar lines, proved that it was indemonstrable. Were the postulate true in the meaning that it was possible to deduce it from the simple definition of the straight line, it must then follow that to substitute any other postulate would involve all demonstrations dependent on the substituted postulate in self-contradictory conclusions. Lobachevsky proved that no such consequence ensued. If we postulate, for example, that two or even infinite parallels to a given parallel can be drawn through one point, the conclusions we shall obtain, however surprising and strange, will be perfectly consistent, and neither contradictory nor absurd. This amounted to a new discovery. It was the discovery that Euclid's geometry is only one of many possible geometries and depends on a choice of postulates. A new branch of mathematical research opened out, and the possibility of non-Euclidean geometries received universal recognition. It was to this study that Riemann devoted himself. He imparted to it, however, an entirely new direction. His guiding idea in working out a complete system of spherical geometry in 3 dimensions was that the dimensions impose limitations or restrictions on the system and determine its degree of freedom. If, for example, we imagine rational beings with length and breadth but no thickness, inhabiting the surface of a sphere, and able to construct a geometry, it is clear that they will attribute to space 2 dimensions, and 2 only. This space will be curved, and they will have no means of knowing it. But as their 2-dimensional space is spherical, their straight line will be curved, for their shortest distance between 2 points will be the arc of a circle. Their space will be unbounded, and yet it will be finite, for they will seem to be able to advance forever in a straight line, and yet their straight line will ultimately return on itself. If now we suppose a 3rd dimension with its corresponding increase in the degree of freedom, then if this 3rd dimension be also supposed spherical, we shall have a 3-dimensional universe which, like the 2-dimensional one, will be unbounded and yet finite. Euclid's postulate will not be applicable. The number of parallel lines that can be drawn through a given point will be neither one nor many, but none. The sum of the angles of a triangle will be greater than 2 right angles, and so on. The significant part of Riemann's conception of his tridimensional spherical geometry, however, is not his proof that it is a workable and consistent geometry, but that, seen from within it, would have, for those restricted by it, the appearance of the unlimited freedom which we attach to the plane geometry of Euclid. It would be impossible for those attached to the system to be conscious that the straight lines in which they would seem to be moving were curves. Einstein's theory is the direct logical consequence of this discovery. Until Einstein, non-Euclidean geometry had been of purely speculative interest. It had not originated in practical doubt concerning the physical existence of Euclidean space. The problem was not posited in that form until the negative results of the experiments to demonstrate the Earth's absolute movement by observations from within the system. No reason for questioning the concept of an absolute framework of the physical universe had arisen. This was the work of Einstein. His theory simply is that our space-time system is non-Euclidean and Riemannian, that it is a spherical, four-dimensional system, unbounded and finite, imposing on us restrictions and at the same time concealing from us our limitations. And his originality is that he discovered the means of bringing this new concept to the test of experiment and applied it to the solution of actual scientific problems. The physics of relativity, therefore, is a complete reversal of the physics of materialism. According to the old science, there is presented in experience an external, extended world, existing in its own right and independent of its appearance to the mind of the individual observer. It was supposed that we learn by experience the various ways in which this world affects us, that we discover by scientific investigation its permanent features and its real attributes, and that by accumulation of observations and direct experiment, we come to learn the structure of the universe, the mechanism of its changes, and the laws of nature. The order of this discovery, according to the old view, is therefore from vagueness to preciseness, by way of abstraction, from the undiscriminated mass to the elements or constituents, by way of analysis. It was supposed that at first there is an undifferentiated perception of external material existence in general, and that by analyzing and comparing it, we arrive at ever more and more abstract principles, and that the more completely we succeed in abstracting these principles, the surer becomes our science. Thus, in physics, we study both matter and form, both quality and quantity, and physics yields to us by abstraction the science of mathematics, which is a science of pure form and abstract quantity. And because of its abstractness, we reach in mathematics the highest degree of certainty. Finally, by means of this analytic abstract method of science, we get the materialistic worldview, a void or expanse from which all objects may be abstracted, but which itself is a homogeneous, immobile, continuous, measurable reality, a matter whose ultimate nature is undiscovered, possibly undiscoverable, but which is distributed unequally in masses in the expanse, and a duration or lapse of time from which events may be abstracted and which is then itself a homogeneous, unchanging, continuous, measurable reality. In calling this worldview materialistic, I do not mean to exclude from it spiritual values. I only mean to indicate its concept of the universe as essentially material and its concept of scientific truth as essentially discovery. The new science of the principle of relativity completely reverses this order and entirely changes this worldview. For it, mathematics does not take its subject matter from physics, but gives to physics the data of all science. The objects of physical science are mathematical constructions. They are not self-revealing objects which we find, they are objects which we have ourselves fashioned out of the events which we coordinate. The proof of this is an appeal to fact and to the nature of experience. The universe consists of events, and we coordinate an event by 4 axes which determine its relation to other events, the 3 dimensions of space and the dimension of time. These axes are determined by a system of reference. Systems of reference are space-time systems. Observers in different systems do not agree in the distance or interval which they assign to the events which they regard as identical for all observers, because each observer coordinates the event for his own space-time. Each space-time system has its own geometry. The relativistic science, therefore, must proceed by determining the geometry of the space-time system in which the event is observed. This is Einstein's principle. How is it applied? Mathematicians since Newton have been continually endeavoring to find a way of expressing the gravitational field in purely geometrical terms, and so making it possible to dispense with the notion of forces acting at a distance. They never succeeded in formulating equations covariant for different systems and so capable of expressing a universal law. Einstein has succeeded by devising a tensor system. Tensor, vector, and scalar are the technical mathematical expressions for the linear directions of acting forces. The easiest way for a non-mathematician to understand what is meant by tensors is to imagine the constitution of an ordinary familiar elastic body, such as, let us say, an India rubber ball. If we take such an object as an example of an elastic body at rest, we may easily understand that it represents for physics an equilibrium between contending forces, the tensile forces acting on the surface and the volume forces acting from within. Now, here of course we are imagining forces inherent in material substance, and therefore to get the true picture of a tensor field we must suppress these and think of the strains and stresses as having their exact equivalent in the actual curvature of pure space itself. The strains or bends of direction due to the curvature of such a space system, as is represented by the India rubber ball, will then be tensors. In Einstein's theory, the gravitational field is such a tensor field. Tensors, therefore, determine the geometrical properties of the gravitational field, and by using them, Einstein is able to dispense altogether with the assumption of interacting masses, and to give an entirely new geometrical formula for the law of gravitation. This new formula, although perfectly simple in principle, is of extraordinary complexity in application. The reason is evident when we realize the peculiar difficulty of the problem. To give the formula of a universal law of gravitation, such as Newton's, when we have no absolute system of reference in terms of which to state it, but only relative systems, each determined by its own coordinates, and all coordinate systems equally eligible, we must be able to formulate laws which are independent of the choice of a coordinate system and covariant with every system. That is to say, the laws, if they are true for one, must be true for all systems, and therefore covariant for each system. This was the problem. The important contribution of Einstein is to have shown that by the aid of tensors, it is possible to formulate such universal laws. The revolution which the theory effects is in the new relation it establishes between mathematics and physics. Every mass of matter, according to the new theory, owes its physical qualities to the geometry of the space-time system which it creates by its movement relatively to other systems. That is to say, matter is itself geometrical. It is not stuff filling space, but itself a humping or warping or twisting of a space-time system relatively to other systems. In the Euclidean geometry, the curvature of space is zero, but according to Einstein's theory, wherever there is matter, there is a degree of curvature. To determine this is to give the law of gravitation. The New World view of the relativist, therefore, is a universe with no stuff in the meaning of the old atomism, no space in the meaning of the old infinite void, and no simultaneity in the meaning of the old time order, in which all events are fixed in a relation of before and after. It is a universe in which there are infinite space-time systems, and therefore a geometry of every point instant. What then is involved in this concept of separate space-time systems if they are to be consistent with the concept of a universe? The reply is that if there is to be physical science, it is necessary that two different coordinate systems shall be completely equivalent. That alone is sufficient condition for the objective standpoint. The universe is one and identical, not because it is independent of every coordinate system, but because each space-time system, while it embraces the whole universe, is covariant with every other. The universe is an objective universe. It is not a dream world or creation of fantasy because, though it is a construction, it is geometrically constructed. The reality of the universe is in, and for those who experience it, its external objectivity consists in the fact that it is measurable, and that the conditions of measurement are independent of the choice of the axes employed. Such is Einstein's theory. Its full significance in philosophy will only appear when we have seen the difficulties in regard to the concepts of space, time, and matter which have exercised philosophers from the beginning of speculation in ancient Greece and throughout the modern period, and even to times present.